All right. Hello, everybody, and welcome to the webinar. I will go over just kind of some common questions really quickly while people trickle in here, and then we'll get started. Uh, First of all, the topic for today is going to be reinforcement learning. So we'll cover a brief introduction to what reinforcement learning is commonly used for, some of the underlying theory, and we'll go into a demo on how you can use the KNIME Analytics Platform to build a reinforcement learning agent in this codeless environment. But before we get into that, I just kind of want to thank you all for coming, and I want to point you to a couple things on the Zoom call. So there should be a Q&A button somewhere on the bottom of your screen there. If you have any questions, feel free to put them in there. You can upvote each other's questions if you want to see those ones answered. We don't have too big of a group, so it should be fine. We'll probably try to get to all of those questions. And I've got two of my colleagues here, Satoru and Lindsay, to kind of help us out there with those questions. So if something particularly relevant to a slide that I'm on comes up, we can try to address those right away. Feel free to save questions until the end if they're more general as well, and we'll have a segment for answering those at the end as well. There was one question a little earlier about a recording for the session. So we will be recording the session, and we'll share that with you guys in our follow-up email, so that'll be available. So no worries about that. We'll share the slides at that point as well. All right. So I guess with that out of the way, we'll get started here. Okay. So I kind of already talked a little bit about what we were going to do today, but just to kind of walk through our agenda. We're going to start out just by kind of talking about reinforcement learning at a really general level. What is it? Why is it cool? When is it used? That kind of thing. Then we'll introduce the concept of Markov decision processes. So these are going to kind of be the framework on which a lot of reinforcement theory lives. We'll introduce a little bit of notation. We'll talk about what policy functions and reward functions are, and then we'll go into the example use case, talk a little bit about how I put it together in KNIME, and then we'll look at an actual demo of it. Finally, we'll conclude. We've got a free book code for you guys to use, and we'll open up to questions there at the end. All right. So first things first, what is reinforcement learning? So it's kind of become a pretty broad field lately with lots of different methods of implementation, and it's used in a lot of different industries and fields and for different purposes. So between that and the fact that just AI and data science and really reinforcement learning as well have become such huge buzzwords, it can be kind of difficult to pin things down. But the kind of big idea behind what reinforcement learning is we're trying to build some agent. So in this little diagram over here, we've got our little robot agent, and he's trying to interact with his environment in a way that maximizes some reward. So maybe if we're talking about just building a human being that survives, maybe that's the reward, just to try to live as long as you can. Maybe that's the reward. Or you'll see some robots that are using reinforcement learning to walk. Maybe the goal is just to keep standing. There's a lot of things that might use just kind of different rewards there. And sometimes those rewards can be difficult to pin down and decide what they should be. And sometimes they're really just kind of served up to you in the use case. Now, this reinforcement learning agent, it could be based on machine learning algorithms. It could be based entirely without them. You could have it just being a set of nested if statements, for example. So really, there's no specific requirement that reinforcement learning is using any of our typical machine learning algorithms, but in a lot of cases, we're going to see that it will, just because of how much power we can leverage there. Now, there's a couple terms I want to kind of point out here on this diagram as well, we've got it. So of course, the agent is just the thing that we're building. It's taking an action inside of the environment that it lives in, and then there's some interpreter, and usually that'll be us, some kind of program we write just to evaluate how well it's done, just to kind of respond to the agent, tell it what's happened in its environment, and give it some kind of reward. So If it finds the candy bar, maybe we say, good job, you found it, and give it some reward points, and then say, okay, that candy bar is now off the board, it's gone. So we're just kind of helping interpret it so that when it takes an action in its environment, we have to tell it if that was a good action or not somehow. Okay. So let's kind of introduce the simplest agent that I could think of. So let's say we're playing a game of rock, paper, scissors, but let's say I'm playing against an agent. Let's put it that way. So I'm playing rock, paper, scissors. I'm playing against our reinforcement learning agent, and it always gets to make its decision after it sees my play. So that's a really easy game to play, right? Because if I throw a rock, you already know that if you want to win, you just throw paper. It's a really simple choice. So if we've got a really simple problem like that, we could build an agent that uses something like a lookup table, right? It's taking an action in its environment to maximize the reward. Maybe that reward is a 1 if it wins and a 0 if it loses, and maybe we'll give it a 0 if it ties as well. So there's a lot of different ways we can construct these rewards, but that's the idea. And then as it goes through and plays, it can fill out a lookup table like this, deciding which different plays that it can make, give it the highest reward. So it knows that if I play rock, it should play paper. If I play paper, it should play scissors. If I play scissors, it should play rock. So this is just an example of how an agent might function, and a really simple example, and one that doesn't use any machine learning. So in this case, we can see that our agent has some way of determining which move it should make. In this case, a lookup table. Okay, so why don't we always use lookup tables? So let's say we go back to that example I used at the introduction there. We have that robot, it's trying to learn how to walk, and it really wants to not fall over. Maybe its environment is a whole bunch of sensors that are plugged into it, and there's just so many different possibilities. You can't really use a lookup table, especially in a continuous and infinite environment like those sensors there that are detecting maybe the angle the robot's standing at, the different accelerations on it. A lookup table really doesn't make any sense in that environment, right? So it really just depends on what environment our agent lives in. So one popular solution to that is to use these neural networks or other machine learning algorithms as well, just depending on what that environment looks like. The benefit here being that we can kind of take all of those details from our environment and use them as inputs into some kind of machine learning algorithm, be it a neural network or something else. This neural network, though, is very popular because of how flexible its inputs and outputs can be. So if we talk about a robot with a bunch of different sensors on it that are all supplying these numeric input values, and that's kind of how our agent sees its environment. It's very natural to use those as the inputs to a network, right? We can use as many of those numeric inputs as we want to. It makes sense, it's easy. It's kind of the standard way to expect to use a network even. There's other algorithms that we can use, of course, those being things like logistic regressions, just regular regressions. There's lots of options there, but the neural network also has a very flexible output, depending on what we want that model's output to look like. It could be an output that looks something like left foot forward or right foot forward, which one? So it could be just making that binary choice, in which case something like the logistic regression would work really well. Or it could be something like what we'll see later, where we actually take an input state of a game board as our agent's understanding of the environment. So a whole bunch of these numeric representations of the environment state. And we then end up with another board state that is also a whole bunch of outputs, which is very difficult to do with most machine learning algorithms. So that's why you'll see a lot of these neural networks being used here, just because of the flexibility of the input and output features. The other advantage that we have with these artificial neural networks is that we can train them iteratively. So this is true of a few different models, but not all of them. Decision trees, for example, we can't really iteratively train because you kind of go through, you use these different counting algorithms to train your model, and then it's just trained. You want to redo that, you have to start from scratch. with a lot of regressions and the neural network in particular, we can use this iterative training approach where we have these preset weights that we just continue to update. So that allows our agent to learn and then go explore some and then come back and learn, and we can iteratively keep improving it that way without having to collect bigger and bigger pools of data to plug into our training algorithm. So those two features, the flexibility and the iterative training algorithm, are really what make neural networks so easy and so cool to use on reinforcement learning projects. Okay, so we talked a little bit there about what it is, but where is it used? So there's a lot of common places where this is used in industry outside of the typical examples that we see all over, like the Medium articles and those kinds of spaces. One of the ones that I've bumped into a lot actually lately is the chemical drug discovery. So normally if you want to generate a new chemical compound that will hopefully be useful in some kind of medical treatment, you would just have to kind of produce a billion different things and just kind of try them and see what works. Maybe you've got some expert opinions from your chemists, and they can make recommendations, and they just kind of go through and they say, I know it needs to have this kind of shape. Let's try producing it and seeing what it does. So what we're doing here with the reinforcement learning is we're allowing this machine learning process, this artificial intelligence here, to go through and for us suggest these different chemical structures that we should try to produce and test. So we allow them to generate a compound, we test its properties, and we update our model. So whenever we have that kind of iterative cycle, we can employ these reinforcement learning techniques. So generate the compound, test its properties, update it, and then the next cycle, hopefully generate better compounds, test their properties, and update. And that iterative process can keep repeating. Same thing with traffic light control. If our goal is to reduce congestion on city streets, maybe we don't want to just have 30-second on, 30-second off green lights. Maybe we want to find a more intelligent way of controlling those lights. So what if we produced an agent who had the ability to manipulate its environment, that environment being all the traffic lights in the city, and its goal was to minimize traffic. So this is another situation where we could use reinforcement learning. We enable this agent to suggest traffic light changes. It employs them in maybe a test environment as opposed to the real world. We can do this with a simulation, of course. We see how much traffic builds up, and then we update our model. And we kind of repeat this and let the agent explore and update itself iteratively. So again, we have a situation where we can go through that little loop there and where we can make suggestions, test them, and update. So these are a lot of the use cases that we'll see. And then, of course, robotics. So we have robotic arms. They've trained different robots that can like gently grab your hand and shake it. They can pick up fragile objects. Lots of things like that have been worked on really for quite a while now. And that can also be done with reinforcement learning. I mean, I wouldn't allow it to actually shake my hand while it's training itself, but we can do a lot of these kinds of things in simulation environments too. Okay. So I see one question here in the chat really quick. And I do want to point out that all of these different use cases that I've exampled, you'll get the PDFs afterwards. And these blue ones here are actually links to published papers on the topics. So feel free to go back into these slides later and check out the links to the papers. Okay, so now we're going to start talking a little bit about some of the theory that lives underneath the hood here. And really the kind of groundworks, the base level that a lot of the other stuff is built on top of is this idea of a Markov decision process. So basically what a Markov decision process means is that we have some environment and it's got different states. In the case of a traffic light, the different states that it could be in are a red light, green light, yellow light. Maybe those are the 3 states that our environment has. And these can be discrete states or they can be continuous states. We can have a finite number of states or they can be infinite. But we do have these different distinct states in our environment, and those are denoted with these S's. And they have different numbers down there so we can tell them apart. Okay. Then we live in this environment state, right? So we get to take actions in it. Now that's the next kind of fundamental concept here with the Markov decision process. We're in these different states and we can take actions from them. And with some probability, those actions could result in different outcomes. And we can kind of look here at this graph again to understand a little bit of what this means. So let's say I'm in environment state S2 and I take action A0. So I've got a 60% chance of just coming back to state S2 and a 40% chance of moving over to state S0. So as far as what those states and what those actions represent, that's not too important right now, but what we want to understand here is that all of these actions that we take, they're not deterministic. So this is a stochastic process, and that's the important thing to keep in mind here, is that these actions don't have definite outcomes. Okay. Just to kind of give an example here, and maybe a slightly more real-life example. One thing that I like to say, well, let's say I'm, actually, I'll get to that one a bit later if we introduce one more thing, so hold off on that one. So this is the idea of the Markov decision process. Just remember that we have our S's symbolizing environment states and our A's symbolizing actions available. And we'll use capital letters to denote all of the possible states and capital A's for all of the possible actions. Okay, so now again, here's just a few more of these notations. So we had the lowercase a representing an action that we can take, the lowercase s representing our current state, so wherever I'm at right now, maybe that means at home. And we have a couple more here. So s prime, so this is the state that we end up in after the action. So for example here, if I'm in state S2 and I take action A0, I could end up back in state S2 again, and that would make it S and S prime. But if I moved over to S0, then S would be S2 and S prime would be S0. So this is just the before and after environment states. Okay, and then we have a little bit of notation down here for reward. We'll cover a bit more detail, and this probability function. So the first one here, the reward function. So this is a really important one because this is what we'll have to build and construct ourselves when we're setting up this reinforcement learning process. And a lot of the times, this can be the hardest part to decide. And now this reward function, it's based on 3 things. So every action has a reward function. So we see that it's based on A, S, and S prime. And in some situations, that basis on A might not make too much sense. Maybe it doesn't matter how I get from S to S prime, but in some situations it might. So one example for that one would be, let's say state S is me being at home, state S prime is me going to work, and there's probably a positive reward function associated with that. Maybe let's call it my paycheck. Now that reward function is definitely determined on some action that I take. Like, how do I get there? If I get in my car and I drive to work, that's good. I probably get most of my reward, my paycheck out of that. I don't have to pay that much to get in gas to get to work. But if my action that gets me from home to work is, I don't know, chartering a helicopter, for example, that's probably not going to have a positive reward. It's probably going to cost me more for that helicopter rental than I'm going to get paid in a day. So keep in mind that this reward function is not just going to be based on our movement through the environment, but also on the action we take to make that move. Okay, the next one we have here again is the probability. So this is just going to be denoted with a capital P. This is the probability that action A moves us from S to S prime. And again, we see that denoted down here in the graph. So the probability that action 0 takes us from S2 to S0 is 0.4. So that's just a way of denoting a lot of the stuff over here in this graph. And again, the capitals here just denote the set of all possible actions and the set of all possible environment states. So maybe all the vehicles available to me and all the different areas in town I might go. Okay. And then having all of that notation now kind of leads us to the next important one. The first one having been the reward function. And we see this pi down here, and this is the policy function. So this is what defines the action that our agent selects. And we'll talk a little bit more about what that means on the next slide, but just keep in mind that our agent basically pulls up a little map here, and it's the policy function, and it determines how that agent will act. So if you've got an agent that's just moving around the grid and its goal is just to get to the reward as fast as it can, maybe its policy function ends up looking like this. It just kind of knows where to go and it tells it what to do. So really, that's all a policy function is it informs your agent what to do. And this is usually going to be something deterministic. So let's say we use a neural network to represent our policy function that informs the action. So at any given input, I should get one specific output, right? So this is just how our agent decides what to do. Now it could be a neural network, it could be some kind of model, it could be that lookup table that we talked about at the beginning. But the policy function just determines how your agent makes its choices. So in some examples, this may be something super simple, like of course, this little flip art over here, or it could be something more complicated, like that giant neural network. So we could use super simple things here, like just always go up. Like that could be a policy function. It can be a constant value, just always move up. We could build an agent that plays blackjack, and maybe it just always says hit me. It's probably not going to win, but it would have a policy function here that informs its action at any given state. Another one that you might see kind of commonly is to take a random action. So this is an interesting one because, of course, it's not going to be particularly performant most of the time, but what it does help us with is it's a useful starting point if we want to train some kind of machine learning based agent. So if I want my agent to play Tic-Tac-Toe, which is actually going to be our use case later, maybe I want it to just play a random spot on the board and see what happens. Just to kind of get some baseline data for it to start updating its network on. And then maybe I'll slowly start adapting this policy function, and then I'll say, okay, maybe half the time make a random choice, half the time do what your network says. Make the choice that you think is best. And this kind of comes into play with a lot of different ML problems, not just in the reinforcement learning space. Because what we're ultimately talking about here is this exploration versus exploitation. When do we want our agent to explore new paths in the environment and kind of find out what happens if it plays the top left corner on the tic-tac-toe board? Or how often do we just want it to play what it already thinks is best? Maybe our network thinks that playing the bottom center space on the board is the best starting position, and it just always does that. It never explores anywhere else. And then it doesn't learn, right? So we need to keep including that random element somehow so that our agent can find these new paths and improve. Okay. So the other big question here was on reward functions. I'll take one moment to look at the questions first. Okay. So I'll do my best to answer that question here on the reward function slide. So there was one question here, but I'll get back to that after I kind of give this really brief introduction of the reward functions. So when we're talking about the reward functions, remember that we said that they were, that they were based on an action, our state, and our next state, right? So it just determines how good of a choice some different move was, right? So there was a question in the chat that was, how do we determine this immediately after the move if we don't know how good that play was? And that's a good example if you're building an agent that plays a board game. how do we know how good moving my center pawn forward is in chess until the game plays out, right? But the catch here is that while it's true that this reward needs to be calculated for every state change and action combination, we don't actually need to know immediately after each move, right? So we can go through, what we can do is we can play out an entire game of tic-tac-toe or chess or whatever our use case is. We can go through and play out the entire scenario, and then we can go back and perhaps in hindsight evaluate those reward functions, because the real purpose of these reward functions is for updating the policy function. So we build these reward functions so that we can go back and in some intelligent manner, perhaps through just running our training algorithm on a model, or perhaps just kind of updating a lookup table. We have all these different options, but we use these rewards functions to influence or change to the policy function. So when we need to have them is when we change the policy function. So in a lot of these use cases, you'll just let your agent go run. It plays, it does its job, it does whatever it's supposed to do. It does that for a while, however long you decide you want to let it go for, and it collects data, basically. It's basically running and collecting data. And then through this concept of the reward function, we label those data points, right? So that we can train some kind of network to kind of understand what boards are good and bad. And this can be a really difficult process, not necessarily technically difficult, but there's a lot of a creative aspect here to choosing your reward function. So a lot of the times when we look up different reinforcement learning agents that play or do anything really, they're usually playing video games. A lot of times they'll play old ones, right? Because if I want my agent to go play something like Pac-Man here, well, there's just a score in the top left corner of the screen, right? I can just use that as my reward function. And it's super easy. It's basically canned for me when I'm playing a video game like this. And that's why you see a lot of different reinforcement learning approaches kind of tested and played with on these kinds of systems, because the reward functions are very intuitive to pick. They're just kind of presented to you on a platter. If we start talking about something like that traffic control or the drug discovery, then these reward functions are less obvious, right? What should my reward function be if my agent is designed to kind of produce good chemical compounds, useful ones? Am I concerned with the average number of reactive compounds? Do I want the to like maximize the number of highly reactive compounds? Maybe some kind of mixture of those reward functions. If my agent is meant to be like guessing yes or no, if I'm building some like agent to look at images and say, is this cancer or not? Should I use accuracy as a reward function? And there's a lot of different questions that come up once we start using these real world use cases. And a lot of those are centered around what should my reward function be? And that's not always obvious. With the example we're using today, tic-tac-toe, that also really doesn't have any kind of scoring system. We can't really look at a tic-tac-toe board and say, oh, that's an 11, right? So we kind of have to get creative a little bit with these reward functions sometimes. So what I've actually done in the tic-tac-toe example that we'll look at in a bit later is, well, you let the game play out, is what I've done. And then I look at the number of turns away from winning or the number of turns away from losing to determine that reward function. If a board was just one move away from winning the game, then I'm going to call that a pretty good board. If a board was one move away from losing, then we'll call that a really bad board. So you kind of have to get creative with these reward functions because we need that numeric representation to update our policy function. Sometimes we even use multiple different reward functions when we're training on more complex use cases. So you might see different like game playing agents where maybe their goal is to kind of like play one of the like an old platformer But we can't really start just by saying, okay, beat the game, clear the first level. So maybe we'll use something like a reward function that is just get out of the first room or move a lot of distance. So we can kind of use these changing reward functions to slowly introduce an agent to more and more complex tasks. And that's definitely a subject of a lot of research lately, and I'm totally blanking on what that's called right now. But if you just look up multiple reward functions, you'll find lots of papers on the topic. Okay. All right. So the next thing I wanted to do was kind of talk you through an example use case where we train a reinforcement learning agent to play tic-tac-toe. So this was all done in the KNIME Analytics Platform. There's no code involved. And what we've done now is we've used a neural network, a Keras-based neural network, to construct our policy function for that agent. So what it's doing is it's looking at all the different possible moves it could make. It's running those through its neural network. That neural network is kind of trying to guess what the reward would be from that move. So how close it would put it to a win or how close to a loss. And then picking the move that puts it closest to winning. All right. And that's kind of the idea there. We just have a policy function that says run the neural network and pick the option that has the highest expected reward. And it plays those games. It then gets that data back, like what we talked about. It finishes the set of games. We calculate the reward based on how close to winning or losing it was. And we train the network underneath just with a supervised approach, right? So that's kind of the idea here, is that this reinforcement learning is just supervised learning with a automatic data collection engine, right? I mean, that's an overly simplified way of saying it here, but that's kind of what's happening in a lot of these use cases, is it's just collecting and labeling its own data. Okay. All right, so before we get into the implementation, I'm actually going to pull up the game here so we can see it, but let me double check the questions really quickly. Okay, so I think I've got both of those. So 1 second while I switch my screen share here. Okay, so what you're seeing here is just the KNIME server web portal. We can build different web applications here, and it's just running a workflow underneath the hood. After we run through this demo, I'll pull up those actual workflows so we can kind of look at them a little bit as well. Okay. So this pops up. This is kind of our intro page. You put some different text in here, a little icon to make it feel like a game and all that stuff. And then you can select if you want to play against the easy mode or the hard mode. And we can select who wants to go first. So when I'm building this agent to play this tic-tac-toe game, it's actually pretty natural to make an easy AI and a hard AI. Because the idea here is that the longer the network trains for, the better it'll be, right? So maybe I let the easy mode agent play for, I don't know, 500 games. And maybe the hard mode agent plays for 5,000 games, right? So there's different ways that we can construct these difficulty scales. Okay. Again, we just kind of move on to the next page here. We've got our little board that pops up, and I'm moving first. So I'm going to go over there. So I can click next. The network will then make some choice about where it wants to play. Let's see if it blocks me or not. Oh, it doesn't, so I just take it. So again, when we're building these agents here, there's always going to be a few gaps here. Let's try playing it again, see what it does the next time. See what happens when it goes first. Okay, so its favorite space is in the center of the board. I'm not sure if there are any tic-tac-toe experts out there. Is that a good starting move? So I'll play down here. Okay, And we pretty much just played this one into a draw. So you can see that we've got this agent here and it's actively playing tic-tac-toe. Is it going to be a champion? Maybe not, but we do have it here and it's playing. So the next thing I wanted to kind of walk you through here was, so there's a question here in the, yeah, looks like Satoru is getting it, but yes, this web portal is part of KNIME server. Okay, I'm gonna switch my screen share one more time. All right, and now I'm gonna walk through these workflows with you. So there's two different ones here. There's the workflow that I've used to train the model, and there's the workflow that I've used to create the web application. And these are going to be available on the KNIME Hub, and there'll be links to them in the slides, and I believe there should also be links in the follow-up email you'll get. So if you want to download these, play with them, try to use it for different tasks even, you're more than welcome to do so. So the first thing we did was define the network architecture that's going to represent that policy function, right? We've got our inputs, our outputs, and some stuff in the middle, right? So this input here is just a 27 length vector, and that's going to represent our tic-tac-toe board. So what I've done to make that happen is, well, there's 9 spaces on a tic-tac-toe board, right? And each one has 3 different options that could be in it. It could be blank, it could be an X, or it could be an O. So if I just kind of unfold that, we get this 27 length vector space. And that's just my input. It's running through a couple dense layers here, not too many, it's a small network, and then outputting what it thinks that reward function will be. So one way to try to play around with improving this process would be to kind of give a bit more care to what our network architecture could be. I mean, that's kind of standard advice for using deep learning in general, but we do want to play with that because we need to find some healthy balance between a network that has the ability to kind of understand the complex problems in tic-tac-toe, I know, but we also want it to be small enough that we can update it and train it in a reasonable amount of time. Yes. Just to walk through these layers again, we've got that 27 vector input space. We're moving that over to a 54 unit dense layer here, which is a hyperbolic tangent activation. We're using this dropout layer. And what this dropout layer does is, at training time, what it's going to do is it's going to randomly zero out with some rate, in this case just 10% of the neurons in the previous layer. And then we're doing that again down here for the second dense layer. And this is a method for regularization in neural networks. And this is helpful here because I don't want my network to get into a rut. We kind of wanted to learn how to generalize and be able to play against human players, right? Because when at training time, it's just playing against itself back and forth. It plays both sides of this board. We want to make sure that it's learning as general ideas as it can. That way it can use them when we talk about letting it play against me, for example, as a person. Okay. And then we're employing a few different loop bodies down here. So this innermost one is a recursive loop. And basically what's happening here is our agent is playing one side of the board, and then the other side of the board, and one side of the board, and the other side of the board, and it keeps going until some game over flag is met. So that could be somebody gets 3 in a row, or that could be all the spaces are filled up. That's how we finish a tic-tac-toe game, right? So it does that in recursion. We get all those board states as an output here. Goes through, we generate those scores based on how close it was to the final frame and who won. And then I'm just kind of doing a little bit of cleanup here to filter it. So that's kind of the idea here, is that we're playing the game in this recursive loop. So again, we don't know what the value of the reward function is right after we make a move. We're not actually calculating that reward until after that game is complete. Okay, then it's inside of a counting loop here. And this is just because I don't think that it's worth updating my network with just one game, right? So I'm letting it play some set of games. Maybe it's, I think it's currently set to 5 so that it runs quickly. Maybe a reasonable number for that is like 100 or something. That way we have a decent bit of data at least to pass to our network learner when we update the model. And that's just going to run through 100 games and kind of compile all of that into one little data table. So what that looks like is something like this. So we've got a vector representing the board, and then we've got these different rewards that we've calculated. So we'll get to that in just a moment. There's a question about activation functions. And I just want to walk you through the final loop here in the workflow. And that's this active learning loop. So this is a reasonably new one. I think it came out early last year, something like that. And what this loop does is it's basically a recursive loop. And its original purpose was to kind of tackle that exploration versus exploitation problem so that we could deploy a model on something, see how well it's doing, and then maybe label some high impact points for it. So it's kind of using that active learning, right? Where we're just kind of carefully selecting which data points we actually want to go through the trouble of labeling. But here what we're using it for is it's basically a recursive loop, except that it has this additional port that represents the model recursion. And that lets me recursively go through this process where I play a bunch of tic-tac-toe games, update my model, pass the model back to the start, and do it again. So we keep doing this. We keep playing 100 games. We keep updating the model, and we keep doing this iteratively. And each iteration, our model should get better and better. And this is one of the advantages of using these networks, is because they're very easy to train in this iterative fashion. We just take those weights from the last when the model was trained, we use them as our new starting point, and then we update them with new data, and we just keep going. And that way we get to continually improve. There was a question about, did I see better results with hyperbolic tangent or ReLU? Hyperbolic tangent is what I've chosen to use in this case because one of the advantages of the ReLU is the speed at which you can train a model that uses ReLU activation functions, because the derivative is, of course, really easy to calculate. So that's one huge advantage of using ReLU, is just the speed at which you can update your network. And in this use case, most of the actual runtime isn't from updating the network, but from actually allowing an agent to play. So this probably takes up maybe 15% of the runtime of the workflow is the actual training of the network. And most of that kind of comes in here when we're playing the games. So in that case, I've chosen to use the tanh, but playing around with different activation functions here is certainly an option. And if you wanted to go in here and just open up this dense layer and change it to use ReLU, you can absolutely do that, and I highly encourage it. And just kind of see what kind of results you get. See if it feels like it's performing better. Maybe add a third dense layer in here, or even just try to widen these ones. There's lots of different options here when we're playing with this network architecture. Okay. I'm gonna call that one. How many games does the tic-tac-toe agent need to play before it becomes perfect? So that's an interesting question, right? So you can talk a lot about that one here. And the real question is, will it ever become perfect? How far should we even bother to train this thing before we see? And of course, because there's a random process down here, we can't say with any true certainty that it'll ever become perfect because we're selecting these moves at random. If those moves somehow ended up being the same moves every single game, then we'd learn nothing, of course. But even ignoring that, we have to consider whether our network architecture is capable of understanding the game tic-tac-toe, right? Is our architecture sufficient? And it's been proven that even with one dense layer in a network, even with just the one hidden layer, if it's wide enough that it can understand any problem that has a solution, but we're never quite sure if our network is wide enough. So that's a difficult question to answer. In this case, I was seeing, and we can talk to this a bit more effectively, I was seeing some drop off in improvement after 1,000 games or so. It doesn't really seem to be improving a whole lot more after that. If I had made my network architecture something bigger, something with more neurons, you could expect that learning curve to probably continue farther. You could continue learning longer, but you probably at a slower rate. So there's kind of a trade-off there. Learning speed versus total potential, right? And that comes down to the architecture. Yeah. So there's two more questions here about the quality and about overfitting the model. So we certainly can overfit this model, and that's one of the reasons for this dropout layer here. And what overfitting means in this case is that it won't know how to play against board states it hasn't seen before, right? We don't want that. And that's a concern when it plays against human players, right? What if I behave in a way that it's totally not used to? And because it's been so hard or so overfit, it doesn't respond to that very well and it loses the game. So that's what we're using these dropout layers for, is to try to induce some regularization into the network and kind of reduce that overfitting risk. The other question there was, oh my goodness, what was it? I clicked that one too soon. Can the learning quality be shown, right? So that's an interesting one. And I've actually stored a collected output here. That's just the error functions here. So on my network. So how far off was my network's expectation of the reward to the actual reward? Now, this probably isn't actually a very good way to evaluate the quality of the network, and that's a really difficult one to evaluate. One way we might be able to kind of graph that out is if after each iteration of this updating process, we had it play against another network that also played tic-tac-toe, but it was static, let's say, and wasn't training itself. And we just see how many of its games it won after one of its 0 iterations, how many games it won after 1 iteration of training, and so on. And that way we can kind of use its win rate against some static opponent to kind of evaluate this. So there are ways that we could do that. But again, kind of like the reward function, it comes down to really asking the question, what does a quality tic-tac-toe agent even mean, right? In a numeric sense. So those are always difficult. So a couple questions here I'll try to address while we're on the looking at the workflow here still. So I actually am producing, the first one here is a question on, wouldn't it be better to give a reward function for every move in the game, perhaps in decaying fashion, instead of just one reward for the win or loss? So that's actually exactly what we're doing here. So these are the entire, all the board states in this game of tic-tac-toe. So there was the empty board, or I think this was after the first move, and then after move 6. So these are all of the board states. So we look at that, and then through this math formula, since the game was won, this winning position gets a reward function of 1, and in this decaying way, the farther from winning the game we are, the lower our reward function for that specific board state was given. So that's exactly what we're doing. And if this had been a loss, I would have given it a 0 down here, decaying again back up to 0.5, based on how far away we were from a losing board. So yep, that is a great way to do it, and that's actually what we've done here. An interesting thing we can talk about from this perspective, though, is some data augmentation options. We could kind of induce more data for training by like rotating these boards, right? And that would help us generalize as well. And the question here about dropout layers. So that, again, is a really difficult question, and it comes down to how aggressively you want to regularize your model. 0.1 is a pretty common start point. And you can kind of try tuning that up and down based on how much overfitting that you want to prevent. Again, a lower R value here will produce a model that trains faster, kind of converges farther, but it won't generalize as well, right? That's the fear. You kind of have to play with that a little bit. Right. So another question down here about the model not seeing much improvement. And again, that was kind of something that was asked a bit earlier. How long does it take for this model to kind of become perfect? And that depends on the architecture. So maybe I'm using a really small network here, just to kind of help it train quickly so that it's easy to run and play with on my laptop. But that might mean that its capacity for learning isn't as deep as it could be. If we used a network with more layers or wider layers, we'd be able to train this agent farther with more games, and we continue to see improvement. But in this case, the fall off with the improvement of our agent is likely because of the small network. Yeah. So there are a lot of different board states for tic-tac-toe. I think it's actually several hundred billion. It would be, what is that? I looked it up at one point, and I can't remember what it was. I know there's just like trillions in chess, and I think there's still actually billions in tic-tac-toe, believe it or not, which makes the lookup table, of course, completely out of the question, even for a simple game like this. Okay. So one more thing I'm going to look at on this one, and then I'll move to the playing workflow. There was a question about how this select move block here works. So these are just components. Again, I put them in this workflow just to kind of clean it up and make it easier to look at and navigate. So if I go inside of this component, you see this in here. So basically what it's doing is it's running all of the possible moves through the network. There's 3 open spaces. So it says what happens if I play on that spot? What happens if I play on the second one? What happens if I play on the third one? And then it generates an expected reward for making that move. And these are what they are. And then it selects the one with the highest expected reward. Now what we see down here is a little bit of row sampling. And what this is doing is it's injecting this random selection. That way, sometimes I just pick a random move, and sometimes I pick my favorite move. And that was our exploration versus exploitation question. We want to make sure that our agent keeps trying different things so that it learns new pathways. Okay. All right. Now I want to also show you briefly this playing workflow. And again, this one kind of operates a lot like the learning workflow, both available on the hub. You can take this one, you can run it on a server if you have one. And if not, you can still run it here locally, actually. You just won't have the interactivity that you would have in the web portal. You'd have to go through and open this up and look at them, which we can kind of do. So actually execute this here, we'll see it. It still pops up with a view. I select it, close it, move on to the next one. Not exactly the way you'd want to experience playing a game, but you can run the workflow and kind of explore it a little bit if you'd like to, even without server. But what we're doing here is we're loading in the only slightly trained model and the more heavily trained model for our easy and hard modes. And then it runs through here. In the learning workflow, the model iteratively plays opposite sides of the board. But in this case, what we're actually doing is every other turn, we just swap who controls it. Up here, we have the select move, just like I looked at in the learning workflow. And down here, we have the option that presents that board that you saw in the web portal and allows the human player to select something. So it just alternates between network selection and manual selection. And that's kind of all that does here. All of these different gray boxes, these components, these represent different pages that you saw in the web portal. So we had this one here again that showed the rules and allowed you to select which difficulty. And then down here, there were the options like, do you want to play again? And finally, just to point out one other thing that I've been doing here is I've been using this web portal application and I've been logging all of these games that are played against real people to hopefully, again, try to further improve the journalization of this agent. So let's just kind of get logged into a table, and then every now and then I go back and I update my network with that data. So you could, of course, update this network kind of live after every game, but like we talked about in the learning workflow, if I've only got 6 data points, do I really want to update a network with 200 neurons? Probably not. So I store that up for a little while and then go back and update the network. Okay. Yep, so there's another question here. Do you just have one neural network for playing tic-tac-toe for the policy function? Yes. So there's just this one network here, and that's the only one. The easy mode and the hard mode are the same network architecture. One's just trained a little bit longer. However, if we want to be really concise about it, technically the policy function is the entire thing that determines which move we should pick next. So really, it's this entire gray box here that represents the policy function. It takes the options, the playable move options, and it selects one, right? Because our policy function just chooses the option that we take. So technically, if I go into this again one more time, our network is just evaluating the rewards from these different possible actions. And our policy function is, first of all, calculating those expected rewards, but then selecting the highest one. So it's really that combination that represents the entire policy function is expected reward and then taking the max. There are situations where your network could encapsulate this entire component. If I wanted my output, for example, just to be the next board, but then we have to get trickier with what reward functions are. So yeah, just keep that in mind. The network is basically the brains of the policy function here, but the policy function itself is really this entire process here where we select the next move. Okay, so I'm going to pop back over to my slides again. And here we see again those 2 workflows where we're defining the architecture, playing the games, and updating the model. And then for the playing workflow, where we just kind of load in those already trained networks, alternate AI versus human player, and then kind of include a few different web pages just for visualization. Okay, we did that a little out of order. I've already seen the demo, that's okay. So just to kind of wrap up here, so we've got a lot of practical applications here for reinforcement learning. Anytime when you can use this agent to iteratively make suggestions, test them, and then update itself, we can kind of employ this process. So it's really a very broad field of applications. We talked a little bit about Markov decision processes, which is just the idea that there are different environment states. We take actions to move around them with different probabilities. We talked a little bit about the policy function, which is just the whole block that says, this is what I'm going to do. It's how our agent makes its choices. We talked about the reward function, which is just how good that choice was, right? And the reward function really, again, I want to reiterate, is commonly the most difficult part of the process here. It can be very difficult to come up with one that makes sense, is intuitive, and also is something that actually helps our network train in a lot of scenarios. We talked about neural networks being a very popular choice, really just because of their flexibility across the board. Yeah, and then we saw a introduction of how this can be done in a GUI tool like KNIME. If you want to check out the blog post on this topic and read a bit more, feel free to check out this link. If you go there, there'll be a lot of kind of further reading options at the bottom of it as well, so I recommend that. Here's the links to the workflows on the hub, and then if you want to connect with me on LinkedIn, you can follow this link down here. And then finally, those use cases that we talked about at the very beginning, the traffic light, drug discovery, and robotics, those pages of the presentation have links in them as well, taking you to those papers if you want to read more about them. All right. So if there are any questions, feel free to use the Q&A tool. We're pretty much wrapped up here. So you can expect a follow-up email with the slides and with the recording. There's a question here. Why did I bother to convert Keras to TensorFlow? So that one isn't strictly required. You can still do that all in Keras if you'd like to. The reason I've done that is because I was using a Java version of TensorFlow for the implementation there, just because I'm using and scoring that network so many times while playing these tic-tac-toe games. It just kind of speeds up the process a bit there if I can run it in Java as opposed to Python. So that was just for a speed increase to make the workflow run a bit smoother. But there's absolutely nothing wrong with leaving it all in Keras. So there's one more question in the chat, and I'll talk about it just a little bit here again. And it was about choosing the reward for a move when it's many moves in the future. So we let with our formal reward function, the one that we supply to our agent, we played out the entire game of tic-tac-toe and gave high scores for moves that were close to winning a game, and gave low scores for moves that were close to losing a game, right? That was kind of how we defined the reward function in this use case. When we're actually deploying our agent and we're talking about that policy function, we're not actually making a choice based on the highest reward. We're making a choice based on the environment state that our network thinks will have the highest reward. So it's trying to use this network to predict what the reward will be before we actually know what it is. And then based on that prediction, make its move choice. So again, when we're actually playing, we don't know the true rewards, we just use predictions for them. And then we generate the true rewards later, and we use those true rewards to update our network and generate better predictions for the next time we play. We're pretty much at time. So there's a post on our KNIME forum if you want to kind of follow up and have more conversation about it. We can do that there. You should get a link to that in the follow-up email. And also just feel free to hit me up on LinkedIn if you'd like to chat more too. So thanks everybody for coming.